Hello there, physics class. I hope that you're having a good day, and here we go to kind of extend lesson 10.1. We had been talking about work, and we're going to extend that to a rate of doing work today. But I want to go back and touch on work just a little bit. We talked about work being force times distance. I want to extend that to graphs a little bit today. If work is force times distance, as long as the force is constant as it's going through that distance. So when we think about a graph, it's another one of those area under a curve type concepts like we had in the other scenario. So you've got the force here, and as long as the force is a constant 50, you can take force times distance as long as it's in the same direction and get your work. We would think about it as being the area under a curve. So we extend it a little bit to think about, well, what if the force is not constant? What if the force is increasing at a constant rate? Or those that are in calculus, what if it's increasing at a non-constant rate? Then you can find the area under the curve with different means than what we're doing here. But for our purposes, since this is not a calculus-based course, we can just use basic formulas like area of a triangle, area of a rectangle, those type of things to find our area under the curve. So this particular scenario would be if the force started at 0 and it increased at a steady rate until it got to be 30 newtons, and during that time that the force was getting to be stronger and stronger, that object moved 5 meters. So what we use is our half base times height to find the area under the curve for a triangle. Base 5, height 30, and that would end up giving you the work for this, which would be 75 Newton meters, otherwise known as 75 joules. So 75 joules of energy would be happening for this constantly changing force that was being applied. Thinking about also work needed to accomplish something, we can say, well, if work is accomplished, you can accomplish work during a certain amount of time. And as that time goes by, what we would call that would be power, would be your rate of doing work. So I have a power, I've got another new unit here, watts. Watts should be somewhat familiar to you. I'm sure that you encountered it anytime you looked at a light bulb at the very least, or if you're familiar with your electric bill, and if you're not because you don't have to deal with that yet, well, eventually those things come up, those type of words. But our power, 1 watt, is 1 joule per second if we're thinking about a rate of doing work. So something could be moving, and it's moving because of a force over a certain amount of distance, but that's happening over a time interval through a certain amount of time. Remember that work is very, very closely related to energy. So when we think about light bulbs and whatnot, you're not really thinking about movement, but you are thinking about energy divided by time. So if you were to go that direction in physics, you would think of power as being energy divided by time. And so you can think of it as that as well. We're going to be mostly focusing on mechanics because that's where we are, but just kind of tuck in the back of your mind that energy divided by time is also power. All right, so we've got, and here's electric motor, but the electric motor is doing mechanical work here. It's raising an elevator 18 meters in 30 seconds. The elevator has a mass of 200 kilograms. How much power is developed for the motor to lift that up? So we're thinking power, so we have an equation for that. Power is work over time. Time, okay, that's great. Time given in the correct units. But what about this work? We need force times distance. We have a distance, but we don't have a force yet, right? So we need to calculate the force. It's a 200 kilogram elevator, And what's happening is that motor is having to defeat gravity, so it's going against gravity. So you're really thinking about what the weight of this elevator is. So force time weight times mass times 9.8. 200 kilograms times 9.8 because the acceleration because of gravity, and that will give you the weight. Weight equals mass times 9.8. So 1,960 newtons is our force in force times distance. 18 meters is our distance in force times distance. When we multiply those together, you get 35,280 joules, so that's your work. And now we can bring in the 30 seconds of time that it took to do that. So the power needed to have that happen would be 1,176 watts. Okay, so that's 1,176 joules per second during the whole time that this is happening. All right, so remember, power is a rate of doing work. We want to think about, again, calculating this based on some changing conditions. The force needed to push a car decreases at a constant rate. So it starts at 500, goes down to 200, and we want to find out how much work was done if the car moved 40 meters during this time. So here we've got a little bit different given and some different things to think about. We want to kind of graphically think about this because you've got the force that starts at 500 newtons and it decreases to 200 newtons. And this is happening right here through this distance. We're not doing power on this one. We're just taking a look at our work. So back to this. Keep in mind when you think area under a curve, sometimes you have to chunk it up. If you want, you could use the formula for a trapezoid, but let's just stick with our rectangle and our triangle because those formulas are very, very simple. So you can divide this up here so you get a nice little rectangle here and a triangle here. So our area under this part would be simply 200 times 40, which gives you 8,000 joules. And your area under this part would give you half base times height. Now be careful with our height. The height is here. I hope you're anticipating that answer would be 300. There would be our height. And our base would be 40. So you'd end up with 6,000 joules. And altogether, our work was the combination of these two. So we have 14,000 joules of work was done. If you wanted to extend that question a little bit, you could ask like something like, if this was accomplished in 14 seconds, how much power was generated during that time? And you would do 14,000 divided by 14 and have 1,000 watts of that was of power for that. So that's just my little brief lesson today. What I'd like you to work on is I'd like you to work on doing the practice problems for the first entire section of Chapter 10. Chapter 10, Section 1. Between yesterday's lesson and today's lesson, you should be able to do practice problems 1 through 12. Tomorrow we're going to work on, hopefully be able to do something with a lab. We'll see how that goes. I'm still debating how to make that happen. I know that some of you told me that you have some stairs at your house, and I don't know how that's going to go as far as other family members being there, but maybe we can at least get a couple of you to be able to give us some data, and we'll set up maybe a Zoom conference tomorrow at about 1:30. And just try to accomplish that and see what we can do and what we can learn during that time. But in the meantime, work on practice problems 1 through 12. All right, I'm looking forward to seeing and hearing from you pretty soon. Have a great, wonderful, blessed day.